Hello everyone and welcome to my talk today. I'm sorry I can't be there in London to present in person, but hopefully you'll enjoy today's topic anyway. For those of you who haven't met me before, my name is Ben Evans. I am a Senior Principal Software Engineer and Observability Lead at Red Hat Cloud Native Runtimes. Before joining Red Hat about 4 years ago, I was Lead Architect for Instrumentation at New Relic, and before that I founded a company called JClarity, which was acquired by Microsoft. Even further back in my history, I spent a lot of time in things like banks, and I used to live in London, where I helped to organise the London Java community. So if you're based in London and you haven't already encountered the LJC, then I highly recommend it. There are some wonderful people there. I have left London and now live in Barcelona, hence travel problems this time. What we're going to be talking about today is the concept of the execution of Java and how it's changed over the years and how it's going to evolve in the future. Some of my recent books cover some of the material I'm going to talk about today, specifically Optimizing Cloud Native Java and the second edition of the Well-Rounded Java Developer. So if you're interested in the topics and you want to dig in deeper, those are probably good places to start. Now, when we talk about execution of Java, I think it's important to be very clear what we mean by that. So in the case of most Java programmers, I think, they think of the Java language, which they type into their IDEs, and then at some point it gets transformed into an executable format. And, you know, it's absolutely fine to work like that and to not think about the other things which go on as part of that transformation and part of that process. But there is actually quite an interesting story here. So to start with, let's think about what the Java language actually looks like. What characteristics does it have? And this is my list. I think other people would have potentially a slightly different list, but this one is mine. I would describe the Java language as quite static. It's statically typed. It is strictly nominal in the sense that all types have names. There aren't no sort of structural types or anything more fancy that you get in other languages. It is very much an object-oriented language, and it sits firmly within the imperative tradition. That's better. Which encompasses both OO programming and procedural. Java, of course, was OO right from the start, but this distinction between primitives and reference types is I think, another glimpse of just how closely it's tied to the imperative way of looking at things. Java is, of course, type arrays. The most classic example of this is Java's generics, which really only exist at compile time. It's not the only example in Java, and of course many other languages are also type arrayed, but Java seems to, for some reason, get beaten up a lot for doing type erasure. I'm not entirely sure why, but that's another story. I would also describe Java as, especially from Java 8 onwards, I mean, there were a few things in 7, and it's getting incrementally better. I would describe it as modestly type inferred. This is not the full-blown type inference that we see in languages like Scala or Haskell or anything like that. More just a way of reducing verbosity and boilerplate without obscuring meaning, I think. So this and the next bullet point where I describe Java as slightly functional. Yes, there are some aspects of modern Java which owe something to the functional programming heritage. But I think both this and type inference speak to the point that this is an object imperative language at its heart, and these aspects have been added in order to make people's lives easier who've come from the imperative standpoint. That discussion about whether Java is a functional language or not, I have another talk about, so if you want to come and hear more about that, then please do. That's the language. But when we actually execute, we of course don't execute Java source code directly. It's compiled to bytecode and then executed on a Java virtual machine, which is a completely different story. The Java virtual machine is a class file-based environment, which is platform independent. I'll say something about that in a second. It involves a bytecode interpreter. So the Java source code has been transformed into this machine-independent format and there are bytecodes which are evaluated in something called a stack machine. What that means is there are no registers. I'll explain a bit more about that when we actually see a little bit of bytecode. But it's not like a hardware CPU. That's the main takeaway here. There are two components which are technically optional according to the virtual machine spec, which are a garbage collector, which reclaims unused memory and makes it available for use again, and JIT compilation, which is a performance enhancement for interpretation. Interpreters are kind of slow, so you can JIT compile and get to native machine code performance. They're both marked with an asterisk because, technically speaking, they are not required by the spec. But in practice, any modern production quality JVM is going to have both of those. So this, as we can see from the bottom bullet point, is a very dynamic world. It's not something which is as static as the languages at all. Just before we want to move on, I want to just cover one point which is mentioned on this slide here, which is the platform independence. So people sometimes ask, why is Java platform independent? And the answer really is this diagram here. Java was first thought of in sort of 94, 95, some ideas in 1993, when the chip landscape was very different to how it is today. I mean, today we have x86 and increasingly ARM chips. But back in the mid-90s, it was much more fragmented. So Java's architecture, where you have a virtual machine, which effectively acts to abstract away the details of the hardware, and a format, what compiler theorists would call an intermediate format, which is the Java bytecode, which can then be executed on any hardware platform, makes sense. This is kind of a long-term bet when you don't know what the future is going to hold about hedging your bets. As it turns out, of course, we have this huge period of time where Intel is completely dominant. So was this all necessary? Well, who knows? Java remains very successful, so I guess it wasn't a bad bet. Let's take a quick look at some bytecode. So here we have a counter, something very simple. We have a class with one field and two methods, an increment and a get. And on the right-hand side here, we can see the bytecode that this transforms into. I like this example because it's actually complex enough that you can see certain aspects of bytecode. Also, if you combine two copies of this running on different threads, you can actually see some of the basics of Java's threading model and some of the things which make concurrent programming in Java difficult from just a class as simple as this. If you're interested in that, it's covered in the Well-Grounded Java Developer. But for our purposes, I just want to show you the nature of bytecode. The first time you see it, it looks a bit alien, but actually once you've learned how to read it, you can see that it's basically a completely one-to-one translation of what's in the Java source code into the bytecode. So for example, at offset 2, we get the field, which we've called I here. We put that on the top of the evaluation stack. We put 1 on top of the evaluation stack above the value of I, and then at offset 6, we add them together. So that shows you the sort of stack manipulations, the evaluation stack manipulations that is part of Java bytecode. So rather than having temporary expressions and registers, this is what we do instead. But once you know about that trick, everything else kind of follows from it. So if you're feeling a bit daunted by the bytecode, don't worry, it really does get very familiar once you start playing with it even a little bit. Okay, so now let's put some of this together and let's see what a modern Java virtual machine looks like. On the left-hand side, we have the creation of class files. Typically these days, this is going to be done not by Javac, but by Maven or Gradle. I mean, under the hood, they're probably going to be driving Javac. But there is some process which is source code compilation. And I'll always say, or try to remember to say, source code compilation, because as we'll see in a sec, there is a different form of compilation which happens elsewhere. Now, the class files that are produced are intermediate format. they are, if you're familiar with compiler theory, people sometimes talk about the front half and the back half of a compiler. Well, Javac, the source code compiler, is like the front half of a compiler. What it produces is a pre-digested form in this well-defined format, which is the Java class file format. At runtime, we need to load that. Now, for ease of transportability and other reasons, we may have packaged the class files up into a jar file or some sort of other archive. But when they come to be loaded into the JVM, they're going to go through the class loader. And everything goes through the class loader. There is no other route in, there are no shortcuts, there are no hidden backdoors. If you want to execute on the JVM, you go via the class loader and you are a class file. And that's true even of dynamically generated code, which is becoming more and more a part of modern Java. Sometimes you're not even aware of it, but there are little classes and little methods that get spun up all the time, both in the JDK and in modern frameworks, but even they must go through the class loading process as well. Assuming you pass the class loading process, and there's a thing called the verifier, which I'll mention again in a bit, the class file is accepted, it's chopped up, it goes into the method cache, which is a piece of metaspace, which we'll talk about again a bit later. And then the methods are made available to the Java interpreter, which is this blue circle here. And code is executing and everything is fine. Now, at the same time that the interpreter is running, so is the JIT compiler. And the JIT compiler is independent, it's a separate subsystem. What it's doing is it has some threads which are watching which methods are getting executed by the interpreter. That's the piece that's marked profiler. And when a method becomes sufficiently interesting or sufficiently called very often or something like that, the profiler will mark it as being eligible for compilation. And then a thread will go and take the bytecode, will compile it to machine code on the emitter thread, and then that will be placed into the code cache as fully finished, highly optimized machine code. And then the code cache will say to the interpreter, we have a new version of this method available. You don't have to use the interpreter version anymore. You can use this optimized machine code version instead. So that is the life cycle of how Java code is executed at a single VM level. And if you look carefully here, you can probably see that there are three of the main subsystems of the Java virtual machine here. There's the class loading subsystem, there's the interpreter, and there's the JIT compiler. The one which is missing is, of course, garbage collection, which we will come on to. I'm not actually going to say that much about garbage collection in this talk. I have whole talks, and in fact an entire training course on garbage collection, but I only have another 40 odd minutes, so not today, unfortunately. So let's take that and let's do a bit of a deep dive on how Java feels about threading. The first thing to say is that, as we've seen, Java is a multi-threaded OS process. All Java programs are multi-threaded because they execute in the context of the JVM. Your program code executes on interpreter threads, which may then be augmented with JIT compilation. But there are also other threads which the JVM uses for itself. So you always execute in a multi-threaded context. Now, you can, of course, create new user threads for yourself. The thread.start call will do that, but you don't have to. Even if you don't, though, the VM threads are still always present. This means that, for example, if you, not that you will ever encounter a machine with only one core anymore, but they certainly were around when I started writing Java. If you take a program which is executing on a single core machine, and you have only one thread of your program execution, and you move it to a machine which has multiple cores, its performance may improve because things like the garbage collection threads and the JIT compilation threads are now able to make use of those additional cores, even if your program code can't. So that is relevant these days in the context of things like containers, which unfortunately are, the details of which are a little bit out of scope for this talk, but never mind. So that notion that a managed runtime can take a previously compiled program, in the sense of a class file, and run it more efficiently on a larger runtime. That's quite important, that idea. That dynamic optimization is key to a lot of what's in the design of Java. We mentioned thread.start. This is one piece of the overall picture here, which is that the operating system creates, manages, and destroys threads. The OS scheduler is something we're going to talk about in depth later, but not now. It's also worth pointing out that the process memory space of every Unix process is standardized, and this goes back quite a long way. So Java programs, yes, because you are executing within the context of the JVM has a standard layout which all Unix processes have, and we have some specializations within it. So as a recap, hopefully this is familiar from operating systems theory. You have a standard memory space that looks a bit like this. You have 4 sections, 2 of which are static, effectively, and 2 of which are dynamic. The 2 static sections are the text section, which contains the binary code. It's effectively the bytes of executable code that are in the binary. The data, which is any static data which is contained within the binary. And 2 dynamic areas, the stack and the heap, which basically control the executing program. So the stack keeps a record of which functions or methods have been called, and the heap is dynamically allocated memory. In C and C++ programming, that is things like malloc and free, but in Java, as we'll see, it's a little different. One other thing that we need to know about is how this picture, this simple map of memory, is actually implemented in practice. These addresses are not physical. They are what's called virtual addresses, and it's the responsibility of a piece of hardware called the MMU, the Memory Management Unit, which takes the virtual addresses which belong to a specific process and maps them onto physical locations. Now, the way that this is done is in such a way that the different processes don't trip over each other's physical memory, so that the same address, I think if I flick between these two, you can hopefully see, the same addresses are mapped to different locations. So the same virtual address in 2 different processes will be mapped to different physical locations by the MMU. There are various optimizations you can do. If certain pages are read-only, maybe you can share them, etc. I won't go into that. But now we can start to talk about the Java process layout. So the Java process layout obeys the standard process layout for Unix, but it adds some additional things of its own. So in particular, we have obviously the text segment with the JVM binary code, and I like to use the terms C heap and C stack versus Java heap and Java stack. So the C heap is any dynamically allocated memory which is done by the JVM. Now, yes, that includes the Java heap where all the Java objects live. That is created at VM startup. It's reserved between this address and that address, and once it's been reserved, nothing else will touch it. Java will not typically seek to allocate any additional memory, and the memory that's within those 2 pointers between the top and the bottom will be handled by Java itself and not by anything else. There are other things in the C heap as well of a Java process. We'll come back to those. Additionally, we have the Java stack frames, and this basically is a way of associating Java methods with equivalent C functions. What does that mean? Well, let's have a look at the stack in a bit more detail. So, as we've said, in any Java process, you have VM threads and you have application threads. Both VM and application threads could be running at any point either a Java interpreter or some native code. So for example, the garbage collector is implemented in native code. So on the left here, something where all the frames are native, that is probably or it could be a garbage collecting thread. There's also JIT compilation. So anything which is running a Java interpreter may actually then JIT compile some of its frames as well. So there is quite a complex question about whether each frame on the stack is a Java frame, i.e. it's running a copy of the interpreter main loop, or it's actually a compiled frame. We'll have more to say about the stack in a sec. Okay, so let's look at the heap. So the C heap as a whole has obviously the Java heap in it. It also has metaspace, which is where the bytecode got loaded. And you might notice that there is a sort of a clustering here, where there are lots of pointers, and they are, at this point, they are pointers, they're not Java references. Java references always point into the Java heap. They cannot point anywhere else, and anything which points out of the Java heap to a different location in memory is not a reference, it's a pointer. So you might notice that there's a clustering of the pointers. We'll explain why that happens in a second. But the metadata for classes lives in metaspace, and there may be further pointers from the class metadata into the code cache or the JIT code cache, which is where compiled methods live. And that's why I always try to say source code compiler when I speak about Javac, because it is something which takes human readable source code and translates it into binary, but what it outputs is Java bytecode. It doesn't actually output machine code. The compiler which is present in the JVM is the JIT compiler, and that does output machine code. So if your definition is produces machine code, it's pretty clear that compiler in this case means JIT compiler. At the bottom, you can also see the off-heap memory. This is increasingly used by major frameworks because they need to have some space to put memory which they're going to manage themselves. Typical example here would be Kafka, I guess, or Cassandra. The Java process layout, this is where the text segment comes in. This is just the bits of the Java binary that have ended up in the text segment. So this is the interpreter, it's the initial or bootstrap class loader, it's the class verifier, which is responsible for making sure that you don't try to sneak malicious bytecode into the JVM, and the garbage collector as well. The JIT compilers will be here, except for GRAL, which is implemented in Java, and so it will be in the Java heap. Okay, let's move on and take a look at objects in the heap as our next topic. Having started with some of the basic components of the JVM, now let's go on to look at runtime behavior. The most obvious place to start is objects in the heap. As Java programmers are familiar with, you have references which point from your local variables in the stack into the heap where the actual objects live. And as you probably know, or I hope you know, Java objects are always referred to by reference. There is no dereferencing operator like the star in C or as you might have in some other languages. You always work by through a reference which acts on objects which are contained in the heap. So let's see how this works. Now as you can see, we have a collection of objects here, and each object is prefixed by a header. As it stands in Java right now, there is no way to construct an object in the heap which does not have a header. And for reasons of simplicity, I've chosen to represent these as two separate machine words. In practice, it's a little bit more complicated, but for now, I think this is a little easier to get your head around for the first time. So let's dive into that. Let's see what's in that object header. So on the left here, we've sort of zoomed in a bit. We have a reference from the stack into the heap, and we have an object. And our two words of header are, well, they're sometimes referred to as the mark word and the class word. The mark word is for object-specific metadata. So this is about metadata which is about this specific object. And if you're wondering why it's called the mark word, you might recall that garbage collection is sometimes referred to as mark and sweep, where any live objects are marked and are therefore safe from collection before the dead objects are swept away. So where do you store the information required to say that this object is still alive? Where do you mark the object? You mark it in its header. So the mark word is there to store garbage collection and other information, but it refers to this specific object. On the other hand, the class word is a pointer, and that's pointer, not Java reference, which points into metaspace. And you may remember that there was a focusing of pointers which point out of the Java heap and into metaspace, which we saw a couple of slides back. Well, that's what these pointers, the class words are. They are pointers, so you can even say class pointer, I guess, which point into metaspace, and they point at a data structure which defines what this Java type looks like. What are its fields and their types? What are its methods? And where is the bytecode or other executable context for them? So this then gives us a model of how we would actually locate a method. So if we want to call a method on an object, a standard virtual method, we follow our reference into the heap, we find our object, we jump over the mark word, we follow the class word, and now we're in metaspace where there are pointers to the actual implementations of methods. That's how it works. And the key concept here is that of a V-table. We have the class word as a pointer to class-specific metadata, and the virtual function table or V-table is the most important metadata that is pointed at. So all methods are going to start off as interpreted, and then the JVM is going to bootstrap. It's going to take those methods which are important, and it's going to turn them into compiled code. So that is the process of JIT compilation. It must not affect semantics. That's very important. But at the same time, it's completely compatible, providing that constraint is met, with the existing interpreter. One other interesting thing about the way that the V-table is structured, which I'm just going to show you on the next slide, is inheritance. Now you will remember that Java is single inherited in terms of class inheritance. Well, yes, there are interfaces as well, but in terms of class inheritance, every class except for object has a single parent, without exception. And this is implemented at a low level in the execution model. So if I have, for example, a class called cat, which needs to, it can purr, it can groom itself, and you need to feed it. And let's suppose, for the sake of argument, that cat is a subtype of pet. So the way that this works is purring and grooming are behaviors or actions or methods which only cats have. So they appear in the part of the virtual function table, the V-table, which is after the pet. And in fact, that is a general pattern. The general pattern is you lay out your V-table exactly the way that your parent class does, and then you add on new methods. So for the cat class, that's purr and groom. So if we want to look up purr and groom as a cat, we go across to the appropriate offset, and there they are. Now, if we want to look up feed, we do the same thing, but here, as you can see, there is a null pointer. So what do? We follow the pointer, which points to our superclass. We go to the same offset, and there we find our implementation. So method overriding for inherited methods in the class sense works like this. Null pointers indicate I don't have an implementation, look at my superclass. So now we basically construct this graph of class heaps, all of which are rooted at the class heap of object. The very sharp-eyed amongst you might notice that there is this groom method, which shows up both for cat and for bear, but at different offsets. I'll come back to that. So here are the 5 invocation opcodes, and this is what a Java language method call boils down into. We have invoke static, obviously calls the static method. Invoke virtual, it's just like normal. Invoke special, this one is a bit of a special case. It's used for calling non-overridable methods, like a supercall to a superclass constructor, for example. We also have invoke interface, which basically involves some shenanigans, because do you remember how groom appears twice in this graph at different offsets? Well, we have to fix that somehow. That's essentially what invoke interface does. And then we have invoke dynamic, which is not only a whole talk, but a whole training class on its own, just to talk about that one. So I will only mention a few things about it. The main ones to focus on today are invoke static and invoke virtual. And invoke virtual, I think, has mostly been discussed in the context of the last slide. So we're gonna move on. We're gonna talk about compilation and compilation strategies, and how these underpinnings that we've talked about actually can be used to put compilation of Java into a broader context. In this section, we're going to talk about 3 of the major technologies which enhance or enable, or words like that, Java's ability to deliver dynamism. The first of which is class loading. Now, we've talked about this a little bit already. The idea is that Java's runtime type system includes Java classes as Java objects. So if you write string.class, for example, you are manipulating a Java object, but it also corresponds to the Java type. That's great, and as we'll see, that has other consequences. But not only that, but we are able to load new types, Java types, at runtime. That's not a new idea. It's been around for decades, and Unix has been able to do it for I think that since the 1970s. But Java enables it in a much more straightforward way. Java class loaders, as well as Java classes, are Java objects. And what that means is we can define our own class loaders which inherit from existing ones. This provides us the capability to extend. We can produce plugin architectures, tools, IDEs, testing frameworks, you name it. This is a huge point of extensibility, and it provides a great basis for the ecosystem of Java tools. But it comes at a cost. And one of the things which we're going to discuss later is how often do we really need this? How often is this level of, for want of a better expression, arbitrary extension really required? Closely related to class loading is reflection. And reflection is, well, what if, given that we have a lot of runtime information, what if we can find something at runtime, we can discover it, and we didn't know we had a class, and then we can use dynamic class loading to get it into the system at runtime. Again, you're thinking about plugin architectures, you're thinking about tooling, which enables us to load things like this. So reflection is therefore several different things. It's the API, it's the technique or the style, it's the bits of the runtime that enable it, but it's also a property of the language type system. So in the reflection case, it's sort of strange, because when you write it as Java code, it looks much more like a dynamic language, because what we're actually doing is we are writing JVM code, not Java source language code. And as we've said, the JVM is much more dynamic, so there's a sort of weird cognitive dissonance there, I guess. But that's kind of necessary, because if we're going to work with arbitrary objects, by definition, that means we don't know the static types. So we just have to work in a kind of agnostic way, because we're trying to build libraries and tools which will work with types that we didn't even know existed when we were writing our libraries. Okay, That's great. If you've played with it, you know how much fun and also how dangerous it can be. But at a low level, it's implemented in kind of an interesting way. So if we have this example here, so we have the entry, and that's short here for map.entry. And you can see that we have an entry object which has a pointer down into metaspace, which is on the lower half of the diagram. In metaspace, we find the class soup for entry, which has the vtable, and then we look across to the right-hand side of the diagram, and we see an entry.class object. That is a genuine Java object. It's not in metaspace, it is a Java object. How do I know that? Because I can write var cl equals entry.class. That's a completely legitimate line of Java, and it will be compiled into something where a local variable points at an object in the heap, and that object is entry.class. However, as all Java objects have a header, we can follow the first word of header, the 0th being mark, of course, down into metaspace. So now we have a situation where we have a class soup for entry and a class soup for class. And what reflection really is imagine that there is a sort of a sideways slicing diagonal mirror here. So that the entries in the vtable in the bottom left-hand corner are mirrored, see what I did there, into the top right. So the entries in the method array are the same, in some sense, as the entries in the vtable. That's why it's called reflection, because we're reflecting back from the vtable back up into the methods. Or in vice versa, if we invoke a method reflectively, each of those methods in the reflective sense, each of those Java objects has a one-to-one correspondence with the actual invocation of actual methods within the VM. We are short of time, so I'm going to skip over the slide. I'm just going to leave it up there for a couple of seconds in case you want to look at it. In terms of how things are implemented, there's actually some interesting stuff there. It's up until Java 17. It changes in Java 18. That's all I'm going to say about it. And instead, I'm going to spend a couple of minutes talking about method handles. So reflection is of its time. It came out in Java 1.1, and boy, does it show. It has a very old API with array types everywhere. No even collections, no lists, for example. Why? Well, because it predates them. When reflection was added, there were no lists. So everything was arrays. So you can dig into each of the reasons that's given here as to why reflection is not what we want to base things on in the modern world. So supposing we were going to take a second bite, what would we do? Well, it might look a bit like method handles. This is a package called Java Lang invoke. There is a class called method handle, and just like with reflection, the instances of method handle represent the ability to call a method. Just like reflection, they're directly executable, and they're sort of similar to method objects. They fix some of the API flaws. So, for example, one particular problem with reflection is handling access control. Because, as you may recall, when you compile code, the Java checks whether you're trying to do anything naughty in compiling code which is going to call a private method. When you load it, the verifier checks and says, hang on a minute, you can't call that. But what about at runtime? What about when that type has already passed through and is in the VM? What about if it tries to call a private method then? So that means that at runtime, any reflective call has to rerun all of those checks. It would be very nice if we didn't have to do that, and that is one of the problems that method handles also solves. There's also some stuff about better type safety in here. I don't have time to talk about that. But the other thing about method handles is that they are also a huge building block technology. We can talk about invoke dynamic, which is the unlocking mechanism for so much of modern Java. We can talk about Project Panama, which is how we connect to better approaches to having native libraries in the JVM be just a natural part of the way that we code. We can talk about some misgun safe, but that again is a talk in itself. We can talk about the way that method handles have been used to replace the internals of reflection without changing the outside API. Could talk about all of those things, don't have time. But now, I think we've got at least a flavour of it, and now we can talk about what a standard lifecycle for a Java application looks like. You know, if this is Spring Boot or anything like this is how it works. You know, you start up, the JVM bootstraps itself, you load up your app, you pull in your jars, you warm up, the JIT compilation, the class loading, the reflection all happens, and we get to this last but one box, the steady state. And this works in a world where your processes are up for a week, months at a time, or maybe they're up, you know, Monday to Friday and they're rebooted at 3 o'clock on a Sunday morning. I don't know. Either way, they're reaching a steady state within minutes. And all of the cost in the warm-up and the loading phases is, we say, amortized over the entire runtime of the process. And that architectural assumption has been baked into Java since the very beginning. But my question is it really true for the world that we find ourselves in today? Okay, so our next topic is reimagining dynamism. And what does that mean? Well, basically, this is the idea that Java is actually quite an old language. It comes from a time when people were thinking about increasingly large footprints of large machines, and by machines I mean bare metal here. And some of the design decisions about being automatically adaptive to take advantage of the capabilities of whatever hardware it found itself on have kind of changed. You know, now we live in a world where we worry about cloud, and are the assumptions and are the behaviors of Java really that helpful anymore? In particular, you know, you might think of, and this is kind of, I guess, one of the simplest examples, things like serverless. You know, in a serverless environment, you start up, you do a thing, you go away. Java's model of you warm up, you reach steady state, you stay there for a long time, and then you close down, those aren't the same thing. So it almost begs the question, when is the cost of Java startup and JIT and reaching steady state and closing down, when is it worth it? Sure, sometimes it's worth it, but maybe sometimes it's not. So then if you're interested in these things, you might ask the question, what can we do to make Java apps start faster? Can we avoid those costs? What are the trade-offs here? Are we using too many resources to provide those dynamic capabilities like reflection and class loading that basically people don't need in the cloud? Okay, that's a great idea. The problem is that so many of Java's frameworks rely upon dynamic techniques. So there is a tension there, and determining how to resolve that is not straightforward. I would also say, and this is one of my things I think I always say, is don't confuse mechanisms and outcomes. People will sometimes say, we need to AOT compile. Okay, why? Well, because we need faster startup time. Well, those aren't the same thing. Faster startup time is an outcome. AOT compilation is potentially a mechanism how you get there, but it may not be the only one. Now, sometimes in technology, we find that there is only one mechanism which brings us to our outcome, but focus on the outcomes first. Okay, sounds great, if a bit theoretical, and what can we actually do that's practical? Well, turns out that we have Quarkus. So Quarkus is, I would say, an extremely interesting project. It's tailored for cloud native, for OpenJDK, Hotspot, GraalVM. It basically has figured out that what we do with cloud-based deployments is that we build an immutable container. and then we ship it to the cloud. Okay, that sounds really simple, but bear in mind that if you're old like I am, then actually we're used to a different world. I'm used to the idea that servers are, something that you lovingly look after and you upgrade its patches and you inoculate it with security patches and you upgrade its version of Java and it's kind of like a pet, whereas these immutable containers are like livestock. Oh, that one looks a bit sick. Shoot it in the head. Get a new one. So the aim here is to do computation once, and people talk about shift left. I've always hated that term because I'm not always 100% sure I know what it means. I think what they mean is you do things earlier rather than later, but I guess it's a marketing term. Anyway, so yeah, so we produce this idea that Quarkus has of a build time. Because what's going to happen? Well, it's going to look a bit like this. On the left-hand side, we can see part of the build process that we've seen before, where we have an app, and we're going to put it into a container, and then we're going to ship that as a unit. Now, the aim here is to provide a choice of deployment modes. We can either do the JVM mode, where we'll be running under OpenJDK, or we can deploy into native mode as well, using the Graal native compiler. There's, I think, perhaps perception that in order to do Quarkus, one always has to do native mode, and that's not actually all that true. I can't share any numbers, I'm afraid, but what I can say is that there are probably less people running on native mode than you might think. There are the majority, and I think I can even say a big majority of people are deploying in JVM mode. So that should also tell you something, by the way, which is that this methodology that Quarkus has of moving computation into the early phases and doing things once, because you're not going to make changes and redeploy. If you make changes, you're going to create an entirely new container image, is remarkably effective even in JVM mode, because that's actually where a lot of the savings come by turning dependency injection and as much initialization as you possibly can into build time, do once sort of activities. So that this is I guess the part that where the elements come together to give you that nice cloud native piece. Now, I was just mentioning about GraalVM. So GraalVM is a project which has become a product, but from Oracle Research. So it wasn't initiated by the OpenJDK team at Oracle, but instead came out of the research labs. It's based around a sort of a slightly, well, I think it's a slightly strange idea the first time you think of it, but if you just at a very high level think about what a JIT compiler actually does, it takes in a byte array, which happens to be formatted as bytecode, so some piece of a class file basically, and it translates it into another byte array, which is machine code for the specific system that you're running on. So that is what it does. It's a function or a method which takes a byte array and returns a byte array. Now, in Hotspot, you could implement that in C++, and currently both C1 and C2, the server and the client compilers, are actually written as C++ like that. But if we just think about a function or method which takes a byte array and returns a byte array, there's no reason why you couldn't write it in Java itself. So you could have a Java method which implements the functionality of a JIT compiler. And that's kind of interesting. It means you have a better programming language to write your JIT compiler in. You can use the same tooling and workflow, so you don't have to jump between Java and C++. There's all sorts of advantages. And of course, and this is probably the slightly mind-bending step, because the compiler is itself a Java method, you can feed it the bytecode of itself. So you can actually bootstrap a JIT compiler by writing it in Java, running it in interpreted mode, but running it on the bytecode of itself to produce a JIT compiled version, and then use the JIT compiled version to compile everything else. So this is kind of the key idea behind Graal, and the thing about it is it also has two modes. So you can use it as a JIT, like I was just saying, but it also supports a native mode, which basically uses the Graal compiler as an AOT compiler to produce Java code which has been compiled to machine code and runs with a minimal runtime. You know, with substrate VM, it's sometimes referred to as, and that minimal runtime contains things like a garbage collector, in much the same way as, for example, the Go runtime contains a GC as well. So we end up with a stack in Graal VM which looks a bit like this. So we have the Java compiler, which is the Graal compiler, and then we can run either with the hotspot VM or in the native image mode, we run with this substrate VM as well. Could say a lot more about this diagram, but short on time, so I'll have to move on. Okay, so let's talk about virtual threads, which is really one of our final topics. So remember what we have said in the early part of the talk when we were discussing the layout of the Java virtual machine and how it executes. All OS processes have what's called a stack segment. This is a fixed amount of memory, which is allocated when you create each thread. So in Java, when you call thread.start, a piece of memory is allocated to house the execution stack rather than the evaluation stack, the execution stack for that thread. It's fixed size, you can't resize it, and it will not get reclaimed until the thread exits. So, and it's not small. So, for example, by default on Linux x64, it's 1 meg per thread. So if you have 20,000 threads, that's 20 gigabytes before you even start. So this basically has a problem that because a Java thread is an OS thread, when you call thread.start, you create an OS thread. If you call thread.start 20,000 times, you are already significantly burdening your JVM. So if you want to have an architecture where you have 1 thread per request, that very quickly becomes a problem. So we call this the thread bottleneck. Now, if we look at this diagram for how threads execute, they're created and go to the ready to run state. The operating system scheduler moves them onto a running state, and then they can give up control in a bunch of ways here. Obviously, they can either die, or they can do a timed wait by calling thread.sleep, or go into an indefinite wait by waiting on an object. So that is the thread giving up part of its time slice voluntarily. The other thing that can happen is the thread can become blocked. This basically is where, let's suppose we're asking the operating system to do something for us, to let us know whether, for example, network I/O would be a great example. So at that point, what's happened is that the user thread is not making progress because the kernel is working on its behalf. So that's kind of interesting, and this will be the mechanism by which we're going to implement the virtual threads. So some basic practicalities: you can get swapped onto a core, you can run to completion purely in user mode, and then get swapped out again. That rarely happens in practice, and instead almost all threads will hit a blocking call. Now the point about those blocking calls is that your Java code is not actually directly calling any kind of what we would call a bare syscall. You're not making calls directly to the standard library or to the actual kernel interface. Instead, we're going to go through some Java code, and it will be the JVM that makes the actual switch into kernel space. So that means that we have a new possibility, which is that the threads, we can have a new kind of thread, which is managed not by the operating system, but instead by the JVM. So they have a shared pool, basically, which they use temporarily every time that they actually want to execute. and the JVM is responsible for managing the multiplexing of virtual threads onto these carrier threads. This has the advantage that we don't have to reserve a stack segment. So we can have as many virtual threads as we like. They are kind of just Java objects. They really only help you if they're going to do some I/O though. If your task is compute bound, virtual threads aren't going to do anything for you. But at the same time, they do feel to the programmer like a thread. So this is the sort of the core of the idea. We're going to sidestep the thread bottleneck problem by sharing carrier threads, which bounds the number of stack segments that we're required to reserve. All the way back in Java 13, some of the groundwork for this was done, and you may not have been aware of this, but Java 13 actually comes with a new implementation of Java Socket API. So if you're running on top of Java 17, you are already running on this, even if you're not running on 21 yet, which is where we get virtual threads. On Java 17, you have the non-blocking implementation of Java sockets. This did not change the API in any way, just why you didn't notice, but it does mean that even when you're making blocking calls in Java 17 or 21, you are actually only blocking from the point of view of user space. The kernel is actually non-blocking I/O internally, because that's how we're going to achieve this magic for virtual threads. We basically are we say mounted onto a carrier thread, and when we execute, when we hit a blocking call, we are going to have the JVM dispatch the I/O call in a non-blocking way, and then yield the carrier thread to a different virtual thread. So that's how we manage it. The JVM is responsible, rather than the OS scheduler, for moving the virtual threads on and off the carriers, and the point at which a vthread has exhausted its time slice, it will be when it makes a blocking call, it will be swapped for another thread. The carrier threads, of course, will receive time slices in the normal way. So if the carrier thread reaches the end of its time slice, it will be swapped off along with its virtual thread. So that's basically how it works. The aim here is, if you are familiar with Go routines from Go, or an Erlang process, which you might find in Erlang or Elixir, it's very much the same idea. And the thing I think which is also interesting, one of the many things I think is interesting about vthreads, is that they have to be specifically created. There is nothing, if you take Java 17 code or earlier and run it, you will never see a virtual thread outside of ones the JVM might create. So none of your existing code will be automatically turned into vthreads. You have to explicitly ask for one using the new APIs. Okay, so now we have this. So I think I've said quite a bit of this. The carriers are a standard Java thread pool. They are just an executor service, but the API has been done quite carefully to exclude a view of what the current carrier thread actually is. So a vthread should be thought of as divorced from any operating system thread. So, yep, they are most similar to Go routines. For a long time, people thought that maybe async await was what they would bring into the JDK. That was considered and rejected eventually. So if I say things like reactive approaches, again, that was considered and not agreed upon. And there's a paper talking about colored functions. If you look at colored functions, that is also something which was not accepted either. You can do thread.yield, but you're discouraged from doing so. Basically, you should let the natural workflow of the blocking calls do your yielding for you. People sometimes ask, what about continuations and things like that? Yes, there are continuations, but they are not accessible for now, maybe not ever, because they're an internal implementation detail as it stands. I should also say that the Kotlin coroutines, which are sometimes considered to be similar, are in fact implemented quite differently. They are implemented as a state machine in the bytecode. If you decompile a class that's been compiled by the Kotlin compiler, which contains coroutines, you will see that the or suspending functions, you will see the state machine present there in the bytecode. This is not them. vthreads are supported at VM level, and they are genuine thread objects, and there is much more low-level machinery going on to support them. Okay, so the future is, I think, still bright. The execution model for Java still continues to change. We are seeing greater and greater strides towards encapsulation by default. That started all the way back with some of the changes which happened in Java 8 and then in Java 9 when modules arrived, but it continues. So we want to see more and more things which are capabilities which are opt-in rather than opt-out. That will include things like security managers being removed, and that one actually isn't. There will be no way in the future to re-enable the security manager. It's actually being completely removed from the code base. Also, things like dynamically attaching Java agents, that will be an opt-in capability. You won't be able to just randomly attach to any old Java process you feel like. You have to explicitly say that you allow that when you start up your Java binaries. We have things like truly final fields, where a final field actually does mean that. It does mean that it cannot be modified even by reflection or other mechanisms. And related to that, we also have what are called stable values, which are coming in Java 25 as a preview, and they provide a way to effectively lazily initialize a field, which is then final forever after. We also have Project Leyden, which is moving, I think, slowly but steadily, and it's producing concepts like a condenser, which is a whole program transformation. It's a standardized way of thinking about how we constrain dynamism, maybe not going as far as full native compilation, which of course would block dynamic class loading and reflection and those types of techniques. But maybe there are other things in there that we can change, and maybe there are some constraints which are separate from the two extremes of the spectrum there. Some of that I strongly suspect, will tie into Quarkus' concepts of build time. Will we see a standardization of that concept? Perhaps. So encapsulation changes are coming. They're there so that you have a rainbow wall of happiness, as this kitten can clearly tell you. So thanks very much for coming to my talk today, and I'm sorry I wasn't there to present it in person.